And we are live. Okay. So I thought I talked to you guys about some things earlier that my second period or my last period class, they did not know what I was talking about. So I want to see if I had talked to you all about it or not. I might have just got sidetracked and not talked to them. But I want to make sure we're all kind of on the same page. So, Leighton, sir, how you doing today?
I'm very good.
Good to hear this, Leighton. So, my first question to you, Leighton, if I have something that I put into a liquid and it is soluble, it dissolves. The thing that I put into the liquid, what do I call that? There's a name for it. Something that I'm
A
going to,
material?
what's that?
A material?
Well, it's a material, but I mean, there's a scientific name. And ladies and gentlemen, I want you to kind of stay away from Googling these answers to these questions because I'm trying to figure out what you guys know and what I've taught you. Um, so, did I ever, Juliana, were you going to say something?
Was it solute?
Yes, it's a solute.
Yes.
So, I put a solute into a liquid, and if it is soluble, it dissolves. If it doesn't dissolve, it's insoluble. So now, Juliana, did you look that up? Did you know that, or did we go over that?
We went over it last class.
Okay, great. I just want to make sure. So then, Jagadish, if I put my solute into a liquid and it dissolves, what is that liquid called?
He left. He left the meeting.
What? As soon as I called him, he
I didn't
left?
say he left the meeting.
He was afraid to answer the question. When we see him, just tell him he was scared.
Oh, he's back.
Oh, he's back. He's coming back. Hey, Jagadish, you can't just disappear when I ask you a question. That's no fair, man. Are you there? So, Jagadish, if I put a solute into a liquid and it dissolves, what do we call that liquid? It's okay. It's a rainy day. Everything's kind of laggy today. No, that is not a solutant. Arsh,
A solution?
no. Well, I'm talking about what the liquid is called that dissolves the solute. Chopper, I see you're on the road somewhere. What is the answer to that question?
Solvent?
It is a solvent. Very good. Um, so a solvent dissolves a solute, and Carson, what does that form?
I'm sorry, can you repeat that?
Sure. So if I put a solute into a solvent, what does that form if it dissolves?
Um, it starts with an S, right?
It does, yes, sir.
And it's not a solvent.
No, well, that's not actually a thing. You have solvent.
Oh, I meant solvent.
Okay, not a problem.
I feel like it's on the tip of my tongue, but I can't remember.
You might have some on the tip of your tongue. I don't know what's in your mouth, but you might have some on the tip of your tongue. All right, so I'm going to ask Akriti.
Is it a solution?
It's a solution. Yeah, it's the three S's. So a solution is made by a solute dissolving in a solvent. Okay. All right. I just want to make sure that we understood um, those fundamental ideas. Okay, so today is going to be kind of a short day. Um, we're going to look at a couple things real quick. I'm going to see if we can guess something. And the biggest thing I want to say, ladies and gentlemen, is one, you guys are wicked smart. Okay, I mean, you know a lot of this stuff already. and I appreciate that. You know, I am very impressed teaching you guys. If you do not know the answers to the lab information that we're going on, I'm going to ask you not to Google the answers, okay? Because we are trying to discover by investigation. If you Google the answers, great. Yes, you know what the answer is. Yeah, and I know I'm a very curious person. I mean, I cheat all the time watching a TV show. I'll Google, you know, what's going to happen in the next 5 episodes, and then I kind of ruin the show for myself. But try not to. But if you do, I mean, we'll still have investigation. But if you Google the answers, do me the favor of not blurting that out to everybody. Okay. Um, I know a lot of the stuff, though. I've talked to some of you individually. You guys know a lot of stuff. All right. But I'm supposed to be doing this trial thing by the book. So we got to kind of, do it this way. Anyhow, enough being said on that. So, sorry, just grabbing a couple things. Well, this is one of my favorite times because we get to play with fire. I get to play with fire. Fire is fun. Fire could be dangerous, but fire is very important to us for a lot of different reasons. Um, Viraj, what is fire?
Fire is like a gas it's like super duper hot and it can like spread really easily.
Okay, it's interesting answer. Unfortunately, not quite exactly true. Jacob, what do you think fire is?
I think fire is like molecules packed super close together, but they're not like super close together, but they're like moving really fast. And then it's like moving so fast that it creates like fire.
So if it creates fire, what is it? What is it creating? What are these molecules creating?
I think it's a gas.
Okay. Shrieker?
I don't think it's really a gas or anything, but I feel like it's the burning or like I could just say combustion of like a material, and it's most of the time it's because of friction. So yeah,
Okay.
and then fire creates heat.
I'm going to ask one more person, and I'm going to ask Elijah. And hello, Elijah.
Hello. So I think it's the burning of molecules. Like if you have like a gas, like some of the gases can burn. Like fire is like the burning of oxygen. I think.
Okay. How about it's a release of energy? I am breaking molecular bonds, and when that happens, there is a release of energy, and that's fire. Kind of interesting, huh? Yes, Carson.
If fire is like a burst of energy, uh, I don't understand how how if you like rub two sticks together, it makes fire.
Good question.
I don't understand how that would happen.
Okay, very good question. Ramchan, how you doing, sir? Ramchan. Question for you. Have you ever heard of the fire triangle? Tell me one part of the triangle. And Carson, this is answering your question here, if you give me a second. Do you know any of the parts? Okay, fair enough. Daniel, do you know any of the fire triangle?
No.
Okay. Anya, how about you? Okay, no answer there. Austin, give me one.
Heat.
Okay, heat. Heat is one of them. Very good. Sid.
So the three parts of the
I only want one
triangle are
though.
heat.
Only give me one.
Oh, you only want one? Okay.
And heat's already been given.
Okay. Fire.
Well, look, we want to know the three parts of fire. One's heat.
Never mind. Heat is fire. Sorry, oxygen.
Oxygen is the second one. And Parneeth, what is one? What's another one?
I was gonna say oxygen, but is fuel one?
Fuel. Okay, I have a match. The wood is fuel. When I strike the match along here, I am creating heat. Put your hands together, rub them. Your hands get warm, right? Friction. It's building heat. So, Carson, I think you asked this. Yeah, like a rug burn. Very good. When you rub two sticks together, is that friction?
Yes.
Yes. So what you're doing is you are generating heat. You have fuel, which is usually little shavings and stuff like that. And now we just need the third part of the triangle, and that's oxygen. And oxygen's in the air around us. Okay. So we have the oxygen. Sometimes you'll see people, they're doing their thing and they're blowing some extra air onto the fire to help it get going. Okay. So I need those three things in a fire for it to burn. Does that make sense?
Yes.
Okay. So I have a flask right here. Now, if I light this match and I put it into the flask, does it go out?
Yes.
It's not going out until I start to burn my fingers. Now, if I do it again, it goes out instantly. Hold on, let's see here. Harrison? So why did I burn it a second ago and it didn't go out, but now I put it in here and it goes out almost immediately?
Because there's not near enough air to keep it going.
Right, and also, did you see the way I held it? I held it this way and it burned for a long time. Can air go in this way?
Yes.
This way, I got a bunch of smoke and stuff up here. I burn out my oxygen really quick. Okay, so I love this job. I just get to sit here and just light match after match after match. But then as soon as I go this way, it puts it out instantly. Elijah, you still can't hear me? You may need to leave and come back. Okay, so I gotta get something real quick. I got my beaker. Let's see, I'm gonna pin this video real quick. Is that better? Elijah, can you hear us now?
Yeah.
Okay, good. Okay, so I have a beaker right here. I'm going to put in some baking soda. Mix it up a little bit. Stir, 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 stir. I'm gonna light a candle. And before I embark on this, why what, Abigail?
I'm gonna go play it. I was just asking why would you light it?
It's because it takes me a long time to strike a match and then do something. It's very easy for me to come over here and just light the match with the fire.
Oh, okay.
So before I do this, Nolan, are you here?
Yes, I am.
Okay, I've got it so I can't see the whole class right now. That's why I was asking. Do we know for a fact right now that any one ingredient by itself does not create a gas on our bath bombs?
No, we don't know for sure.
We don't. Didn't we test each one of our ingredients in water?
We did. Oh yeah, we did with the chart. So yeah, we do know, and that was citric acid.
Well, none of them created gas by themselves. They all dissolved or they didn't dissolve. You know, they were either soluble or insoluble. But now what happened is then we started mixing things together. And we found that gas was produced by
Citric and baking soda.
citric and baking soda, and what was the other one?
Lemonade and baking soda.
Right. And lemonade contains citric acid. All right, so what I'm going to do is I'm going to take some citric acid. I already got baking soda in the water. I'm going to light my match. Dump this in here. And notice, as soon as I put the match over here, the match goes out. All right. So, now,
I think I know why.
Why?
Because sometimes if you blow too much into like a match, it will go out because of how much oxygen you're putting in. So is that why?
Nope.
Okay.
All right. We know fire needs three things. We know it needs fuel. We know it needs heat. And we know it needs oxygen. Correct? So if my fire has gone out, I have lost one part of my fire triangle. I had enough match left, and there was heat because there was already fire. So I'm frozen for some of you, huh?
You froze
Yeah,
up?
couple seconds.
Yeah, you froze up for a second.
Okay. So what I was saying is, for that to go out, I had to lose one part of the fire triangle. I had to lose oxygen, heat, or fuel. Well, my match had plenty of fuel left. I had heat, but did I have the oxygen?
No.
Most likely not. We already know that when I do the reaction, I lose mass, correct? I mean, when we did this in an open container, I lost mass. So we know gas is escaping out of the flask. Is that not correct? Or is that correct? So chances are the gas that is coming out of there is replacing the oxygen. Now, what I want you to do is, if you look in the Google Classroom, I'm going to present my screen real quick. There is this chart right here. Open, open, open. Waiting, waiting, waiting. Okay, can you all see my chart?
Yes.
Yeah.
Okay. And like I said, you also have this in the Google Classroom. So these are common gases found in our air, in our atmosphere. We have nitrogen, oxygen, argon, carbon dioxide, neon, helium, methane, hydrogen, propane, carbon monoxide, and then air. And if you look at the next column, it tells you, okay, nitrogen is 78%, oxygen is 21%, argon is approximately 1%, and from there it gets down smaller until you get down to air. And air, it says not available. And the reason is because all those other gases make up our air. And there's other things in there, but these are the main gases that we're going to talk about. The next column, it says boiling point in Celsius. And you can see that the warmest temperature where something goes from a liquid to a gas is propane at minus 42 degrees. You don't want to be in minus 42 degrees. It's cold. It's very cold. So everything else, I mean, all these things are in gas at temperatures that we live in. Okay. And carbon dioxide, it says change straight from a solid to a gas with no liquid phase. And this occurs at minus 78 degrees Celsius. 78.4, excuse me, be more precise. And the thing I want to talk to you about next is density. Density is a measure of how much stuff, how much matter, how much mass is in a given amount of space. And in this chart, we are talking grams per liter. Typically, we measure density grams per milliliter. But with the air, we're talking grams per liter. So we can see that air is at approximately 1.160 grams per liter. That's the air that we live in. Anything lighter or anything less should float or should go above, should rise ahead. We call that, or above, we call that floating. If you look at helium, helium has 0.179 grams per liter. Helium is less dense than air, so helium rises. Now, we just saw an experiment where I mixed citric acid and baking soda in water and it produced a gas. And I lit a match above the flask and it extinguished the flame. So if we look at this last column, it tells me nitrogen, argon, carbon dioxide, neon, helium, and carbon monoxide will all extinguish a flame. Some of them are less dense than air, meaning they will rise. And some of them are heavy, meaning they will set. Now, can I pretty much guarantee at this point, and I will ask Joshua, are you with us, Joshua?
Yeah.
Okay. So I see that oxygen, methane, hydrogen, propane, and just regular air will all allow a flame to either increase, explode, or go from a glowing ember to a flame. Can I pretty much guarantee that the gas being made in my flask is none of those?
Yeah.
Yeah, because my match went out, right? Okay, what I want you to do, I'm going to close that right now. I am going to maybe somehow come back to my Google Meet for a second. Let's see, what did I mean? I froze again. If you look at the Google Classroom, you can also notice that Mr. Yes, I did change the theme just to make it easier for me to find each one of the different classrooms. I'll come back to that in just a second, Sahana. All right, what I want you to do is, let me stop presenting real quick. You don't need to see my inner workings. I'm going to post a question that I would like you to answer. Stupid picture is in my way. It's a picture of me. Nobody wants to see a picture of me. Surprised I haven't cracked all your computer screens so far. Your question that I want you to ask or answer, if the match went out above the flask, which it did, was the gas produced more or less dense than the air, and why? It's a fairly simple question. I want you to answer this question and also possibly write down some of the gases you think it might be. Remember, no Googling, but I want you to explain why you think the gases are more or less dense than air and why you think maybe the match went out. I mean, what gases could possibly have caused the match to go out? I just posted it right now. Oh, wait, did I?
Yeah, it's in a week.
It's where?
It's in classroom, like week 12.
Why am I not seeing it here? Hold on a second. Maybe I just need to refresh my
I can
screen.
see it. I can see it.
I think I just needed a refresh. Yeah, my computer's starting to. Okay, yeah, there it is. Okay, great. Okay, so answer that question. And what we're going to do on Thursday is we are going to investigate some of the different gases it could be. Now, I wanted to address Sahana's question here real quick. So a cup of water that is frozen is more dense than a cup of water in liquid form. Yes, and we know this because we go back to our states of matter. All right. So if density is based on how much mass is in a given amount of space, volume, we know that when something is in a solid form, the atoms are closely packed together and they're lightly vibrating, correct?
Yes.
Okay. So we add thermal energy. And the first thing that happens is the molecules start to spread out. So if that's the case, do I have the same amount of space in the same amount of volume? If they've already started to spread out, hasn't my volume increased?
Well, the molecules have spread out, which means yes, it did.
Right. And I keep adding more and more thermal energy to the atoms, they turn into gas and they really expand. So then I have less amount of atoms, less amount of matter in that very specific given amount of space. So my density gets less. So as I add thermal energy to something, as it gets warmer, as it gets hotter, its density becomes less.
Oh.
Now,
Oh, okay.
maybe I asked this to you guys before, maybe I didn't, but how many people have ever seen a lava lamp? You know, lava lamps are kind of cool. What you do with a lava lamp is, for the most part, a lava lamp is water, colored water of some sort, and oil mixed together. And in the bottom of the lava lamp is a light bulb. So the light bulb is heating the water and heating the oil. And when it's down by the light, it becomes less dense. So either the water or the oil rise up. As it gets close to the top, it loses its heat, so it comes back down. So you get this fluctuating oil and water going back and forth, which which lets people sit there for however long they want to, watching this lava lamp just do its little thing. And all it is, it's simple science. It's just two liquids with changing density. And some guy figured that out and made millions of dollars. It's kind of neat in my opinion. So, does that all make sense? Yeah.
Is this question for a grade?
Yes, it's part of the lab grades.
Okay.
Leighton, you have 2 lava lamps. That's pretty awesome. Well, I figured you were just really excited and screaming you had 2. Okay, ladies and gentlemen, that's it for today. When we come back on Thursday, we're going to experiment with at least 2 different gases and see what we can do from there. Answer that question, and I will see you guys on Thursday.
Bye, Mr. Schillinger. Have a great day.
Bye. Friday is a B day. Yes, Jagadish. Bye, everyone.
Bye, Mr. Schillinger.
You guys be safe. Come back and see me. And I will have this video posted here in just a little bit. Bye.